Hey kids, reading one of the best biographies of all time, Prehistoric Life, an overview of life on Earth. What an amazing story. And I would say, looking back at the history of life on Earth, may be one of the most relevant things we could possibly do. Because you see, the fossil record indicates that life is a challenge. 99.9% of all species that have ever lived are now extinct. So what can we learn from the Earth's past so that we can plot our course into the future and survive? Construction. A big part of the story of the Earth's history was discovered accidentally in the early 1800s and late 1700s by an English surveyor named William Smith. So William Smith was a surveyor who dug a canal. He could tell what depth he was at in the rock based on the fossils that were there. And within layers, he also saw changes in fossils. We call that faunal succession. And geologists built on William Smith's concepts, and they added era boundaries which were marked by major changes due to extinction events. So another principle that helps us to unravel the Earth's history is the law of superposition. You can tell the order at which rocks were deposited, which ones are older than which, based on their position. So this layer is the highest. That's going to be the newest. The farther down we go, the older the rock gets. So this layer is younger relative to this layer. So we call that relative dating based on the law of superposition. Now, if I use radioactive isotopes to measure the actual age of these rocks, that's absolute dating. So I can use radiometric isotopes to measure the exact age, or I can just compare their position with the law of superposition to see how they are relative to each other. One way that scientists learn about our past climate is ice. They drill ice cores in the Arctic ice sheet, and from that ice they can look at the bubbles and figure out what the composition of the air was, such as CO2 and nitrogen, oxygen. They can look at the dust and they can analyze volcanic eruptions that occurred that produced that dust. They can get an idea of wind direction and how much precipitation fell, because they can tell the difference between snow that fell in the summer and snow that fell in the winter. So another way that scientists can tell past climates is by taking bivalves or brachiopods. These once lived in the ocean, and basically when this organism was alive, it absorbed oxygen from its environment and it formed the shell. There's two types of oxygen. It's oxygen 18 and oxygen 16. They're isotopes of each other. Oxygen, they both evaporate in water, but oxygen 18 doesn't make it as far. It's going to be more likely to come down in rain, be washed back into the ocean. But oxygen 16 is going to make it farther. It's more likely to make it in farther northern latitudes and come down as snow and ice. So what happens is, over time, if it's cold, in cold climates, oxygen 18 builds up relative to oxygen 16 in the ocean. So you're going to see more oxygen 18 in seashells when it's cold. When it's warm, the snow and ice melts and oxygen 16 returns to the ocean, and so the level of oxygen 16 and 18 in the seashell are going to be closer to each other. So one way you can tell about a past climate is the evidence of glaciers. So this big rock that I come across when I take my dogs to Keener Park is really unusual. It's not like the other ones. This is actually granite. And whereas all the other limestone is like these flat sheets, and they have fossils in them. I'm not a geologist, but I'm pretty sure that's granite. And if so, this is igneous rock. It came from a volcano, and I suspect it was pushed here by a glacier. We call that an erratic. So glaciers, because they're giant bulldozers, they leave evidence that they've been in a location, and that tells us if there was a glacier, it was cold, and we know that it was cold in Ohio. So glaciers are evidence of climate change. So why am I wearing sunglasses and a helmet? Well, this is the Archaean Eon. The Archaean Eon begins with the end of the bombardment of the planet by comets. It's super hot. There's volcanoes everywhere. I've got to protect my head from falling lava chunks. The Archaean starts 4 billion years ago and goes to 2.5 billion years ago. At 3.5 billion years ago, in the fossil record, we see the first organisms. What are they? Wait for it. We expect them to be simple, and they are. They're anaerobic bacteria. How could they survive back then? Scientists think that they survived the way they do today. They survived off of the gases coming out of volcanic vents. Today, when we go to the bottom of the ocean, to our surprise, we find whole ecosystems that are based on bacteria living off of the gases coming out of volcanic vents. We call them chemotrophs. They're using chemicals to generate sugar. The next eon is the Proterozoic Eon, which begins with an oxygenation event. The first bacteria were living off the gases coming out of the volcanic vents. The second bacteria group, the cyanobacteria, were actually photosynthetic. So within that time, it appears that the ability to undergo photosynthesis had evolved. That oxygenation event comes at the same time that stromatolites appear in the fossil record. Stromatolites are colonies of cyanobacteria that can undergo photosynthesis. This is another pattern of evolution. Every once in a while in the fossil record, a new innovation pops up and makes a big impact. But about 2.4 billion years ago, things started to get cold. Scientists hypothesized that the stromatolites, because they were undergoing photosynthesis, were absorbing carbon dioxide, a greenhouse gas, and in turn that was cooling the Earth's atmosphere. Toward the end of the Proterozoic, we see the first appearance of multicellular marine organisms. From fossils in Australia, it appears that the very first multicellular organisms were simple things like jellyfish. The next eon is the Phanerozoic, which is Greek for visible life. So the Proterozoic, which means former life or previous life, had been mostly microscopic. But in the Phanerozoic, life becomes multicellular and becomes visible. The first period of the Phanerozoic is the Cambrian. The Cambrian is famous for the Cambrian explosion. It's not a literal explosion, but a figurative explosion of life. Where? In the ocean. Life starts out in the ocean, and we call it an explosion because you pick an animal today, with a few exceptions, and you can find its relative in the Cambrian. Now, they won't look like today's animals, but they will be primarily invertebrates and marine life. So marine invertebrates, animals without a backbone. We know the Cambrian primarily from the Burgess Shale in the northern Rockies. Originally, the organisms were at the base of a sea cliff, and eventually that sea cliff, base of that sea cliff got lifted up about 8,000 feet into the Canadian Rockies. What was the Cambrian like? Well, check out my gear here. The Cambrian was super hot. Carbon dioxide levels were 15 times today. The average temperature, scientists think, was between 122 and 140 degrees, really hot. Why did life explode in the sea? Couple hypotheses. There was no plant life, so scientists think there was a lot of erosion of minerals into the water, which marine invertebrates were able to incorporate to evolve exoskeletons and shells. Also, there was an increase in phytoplankton, microscopic ocean organisms that undergo photosynthesis and form the base of the food chain. So that increased the level of oxygen given off in the water, which is a good thing, plus it helped the food chains. Cambrian explosion. The next geologic period after the Cambrian is the Ordovician. Take a look at the rock around you here in Cincinnati. This is all Ordovician. Pretty amazing to think that this creek bed that I'm walking down was once the bottom of the ocean in a coral reef south of the equator. What do we see? Almost all marine organisms. The Ordovician continued the Cambrian, but we see a new pattern of evolution, diversification. So the organisms that showed up in the Cambrian, by the Ordovician, they diversify. There are more of them. How does that happen? It happens through the process of mutation. As DNA changes, we get new species arising from previous species. So there was a diversification of marine life, and if you look at the fossils here in Cincinnati, like this horn coral, we used to be a tropical shallow ocean. We used to be a coral reef slightly below the equator here in Cincinnati. Big event in the Ordovician. We see a record of the first jawless fish show up in the Ordovician. Toward the end of the Ordovician, we have a change, a drop, a plummeting in temperatures. And at the end of the Ordovician, we have the snowball Earth, a plummeting of temperatures, a drop in CO2. And there's evidence of glaciers at very low latitudes close to the equator in Africa. And so that's evidence that there was glaciers from pole to pole, and this caused an extinction event, one of the first extinction events, which is another pattern we'll see in evolution. Every once in a while, things get crazy and life takes a hit, takes an extinction event. The next period is the Silurian. Well, toward the beginning of the Silurian, things got warmer, and the Silurian was a very consistent period. It was good for life. So life continued to diversify in the sea, and it was so warm, no ice caps, that they found coral reef fossils as far as 35 degrees north, which is pretty far north. That would be like between Georgia and South Carolina. You don't usually see coral reefs there. Also, during the Silurian, the first land animals show up in the fossil record, which some of the first ones were, oh, that's nasty, primitive scorpions show up in the fossil record. So the first organisms, the first animals on land were the arthropods, those with jointed appendages. Also, those simple plants of the Ordovician, by the Silurian, they become complex. Another pattern we see in evolution. Things become more complex. By the Silurian, plants were vascular, which means they had tubes running up through their body, tubes running up through their stem that could transport water. So they were able to get taller as a result of this vascular tissue. So the Silurian was a good time for life. The next geologic period is the Devonian, known as the Age of Fish. Again, this pattern of evolution. The fish that show up in the Ordovician, by the Devonian time, they've diversified into many kinds of fish. The Devonian is also known for the first fossils of tetrapods, four-limbed animals that crawl up onto land. What were they? They were the amphibians. Amphibian means double life, because amphibians live part of their life in the water and part on land. Scientists think that they made the transition from ocean to freshwater, rivers, and then on to land. There are actually fish like lungfish that actually have lungs and gills. By the Devonian, there are actually forests on the planet. And those forests began to reduce the amount of CO2 in the atmosphere, a greenhouse gas, kind of like the stromatolites did. So we see a repeating pattern. There's a drop in temperature because of the forest. And there was also a drop in the ocean oxygen, which caused an extinction event toward the end of the Devonian. So what we see in the fossil record is this pattern. Sometimes a few species can have a big impact on the planet. So the Devonian, the age of fish had diversified. Actually, piranhas weren't there, but the next period is the Carboniferous, which means carbon bearing. That's where we get a lot of our coal comes from the Carboniferous. During the Carboniferous, there were widespread swamps, and the trees in those swamps had chemicals that prevented them from decomposing after they die. So rather than decomposing, the trees were converted by heat and pressure into coal that we're using today. There were also, the Devonian forests had continued to expand, so during the Carboniferous, temperatures dropped, as did CO2 levels, so the Earth continued to cool, become cooler and drier. But during the Carboniferous, there's a significant adaptation, or we call it derived character, shows up. The amniotic egg, cheer for it. Reptiles had shown up as well as the amniotic egg. Why was that key? Because the amniotic egg can be laid anywhere. It doesn't have to be laid in water like amphibians do, because it won't dry out. So the amniotic egg allowed reptiles to invade the land and spread away from sources of water. So we get the first reptiles that show up. Forests are widespread. Carboniferous was a pretty good time, except toward the end of the Carboniferous, all the continents had come together to form a supercontinent called Pangaea, which is going to have a big impact in the next geologic period. The next geologic period was the Permian. So during the Permian, Pangaea stretched from north to south of the equator, this supercontinent. And that supercontinent had a big impact on life. It was a tough time. So as the continents came together, around the continents, we tend to have coral reefs, which are like the rainforests of the sea. But as the continents smashed together over huge amounts of time, all that habitat was lost. So there was a drop in the diversity of marine organisms on the planet. Also, Pangaea disrupted ocean currents because the ocean had to flow all the way around. So the Permian was a pretty tough time on life as the climate got drier and more arid. But the reptiles continued to diversify because of that amniotic egg. Reptiles began to become more mammal-like. The synapsids, the mammal-like reptiles, over time their limbs went from the sides of their body more underneath, which made them faster, more efficient predators. We have a really good record of how the inner ear of the mammal evolved. See, we have 3 bones in our inner ear, reptiles have 1. So what the fossil record shows is that in reptiles, a bone from the top jaw and the bottom jaw got co-opted and became part of the 3 inner bones of mammals, and mammals have much better hearing than reptiles. Another example of a pattern of evolution. Things become more complex over time. Why am I wearing this hairdo? Because, wait for it, during the end of the Permian, things got downright hairy. So Pangaea had caused all this disruption. And if that wasn't enough, in Siberia there were huge volcanic eruptions that occurred over a long period of time and released gases into the atmosphere, which scientists believe had an impact on the quality of the atmosphere and the ocean. So if you're around during the Permian, it would have been difficult to breathe. So this led to the Permian Extinction, also known as the Great Dying, the single biggest extinction event in Earth's history. 95% of marine species and 70% of land species went extinct. But don't fret, life is going to bounce back. The end of the Permian marks the end of the Paleozoic era and the beginning of the Mesozoic. Paleozoic means Ancient life, Mesozoic means middle life. Another pattern we see in evolution is adaptive radiation. After an extinction event, there are roles left open in the environment, niches as they're called. And what happens is the animals that are left, the animals that survive the extinction event, adapt, that's where we get adaptive, and radiate into these new niches or roles. But in order to fill these roles that they're not quite right for, they have to evolve. The ones that evolve slight changes adapt into these new roles. So after an extinction event, we usually see adaptive radiation. In this case, it was the dinosaurs that underwent adaptive radiation. At the beginning of the Triassic is the first period of the Mesozoic. We also see the first fossils of mammals. Not like the mammals you know of today, but small mammals, insectivores, mammals that were running under the feet of the dinosaurs. The Triassic was a dangerous time, so you would have had your weapons and looked up in the sky, because we get the first flying vertebrates. What were they? Not birds. They were the pterodactyls. So dinosaurs had taken to the air, and the pterodactyls did really well. So during the Triassic, we see again this pattern of evolution, diversification. So the dinosaurs at the beginning of the Triassic begin to diversify, and then there's greater variety of dinosaurs by the end. During the Triassic, temperatures went way up, so there was an increase in carbon dioxide, possibly due to volcanic activity, and there was an extinction event toward the end of the Triassic. The second geologic period of the Mesozoic era, Mesozoic meaning middle life, was the Jurassic, from which we get Jurassic Park. It was a good time for life on Earth. It was warm, it was humid, the dinosaurs were flourishing, and we get another evolutionary innovation, adaptation, shows up in the Jurassic. It's the feather. Scientists believe the first feathers were actually meant to keep dinosaurs warm. The very oldest fossilized bird is Archaeopteryx, ancient bird. And there have been specimens found in Germany, and scientists believe that they crawled up trees and they glided from tree to tree. Warm. Anyway, over a long period of time, the feathers evolved to enable flight as well. Interesting late breakthrough in 2017, Dr. Chuang from Southern California University took an alligator embryo, tweaked the genes, and got the genes to produce on scales a primitive feather. So scientists believe that feathers evolved from scales over a long period of time through mutation, and it enabled the dinosaurs to initially stay warmer and also eventually to fly. Also during Jurassic, a key event occurred. Pangea began to break apart, which was good for life on Earth. We also see an increase in insect diversity. Again, this pattern of evolution, this increase in diversity over time. The Jurassic was a good time for life on Earth. The last geologic period of the middle Mesozoic era is the Cretaceous. The name comes from the extensive chalk formations that we have that form as these marine organisms evolved during the Cretaceous, and when they sink to the bottom after they die, their shells become chalk. During the Cretaceous, dinosaurs continued to do well, and we get a new evolutionary innovation, the flower. The first flowers show up in the Cretaceous. So flowering plants are one of the later plants that show up in the fossil record. And with those flowers, we also see the first fossilized bees that would pollinate those flowers. During the Jurassic, we also see more of this evolution of dinosaurs developing feathers. Some of the best fossils of dinosaurs with feathers are found in China. But why am I wearing the wig? Well, toward the end of the Cretaceous, it's gonna get hairy. So at the end of the Cretaceous, an asteroid came through the Earth's atmosphere that was enormous. It didn't burn up, and it hit the Yucatan Peninsula and created some major chaos. In fact, around the world there is a layer of iridium which comes from meteors, And that layer of iridium, below that layer of iridium, we see dinosaur fossils. Above it, we see none. So apparently that asteroid obliterated the dinosaurs, and we can still see they've mapped the impact crater in the Yucatan Peninsula in Mexico. But you know the pattern of evolution. You know what's coming. Life is going to bounce back. The Cretaceous was not an easy time. Reenactment. The first geologic period after the extinction of the dinosaurs, we get adaptive radiation. This time it's Team Mammal. Team Mammal, your class, begins to diversify during the beginning of the Paleogene, the first geologic period of the Cenozoic, which means new life. So the mammals began to diversify, and a key evolutionary innovation shows up: grasses. As the Earth's climate became drier and cooler, grasses were much more adapted to that type of climate. And along with the grasses comes the first fossilized evidence of the grassland mammals that ate those grasses. So there was a major change in the Earth's climate. During the first part, for about 10 million years, there was a major fluctuation in the climate of the Paleogene. At times it was warm and then cold. So the Earth went through these climate shifts, and the Earth was slowly transitioning from a greenhouse world, the greenhouse world of the Mesozoic, to the icehouse world that we live in today. The continents were getting closer to where they are today. And a major geologic feature was when India plowed into the Asian plate, and as it pushed up, it created the highest mountain chain in the world, the Himalayas. And in the Himalayas, we have fossils that came from the seafloor during the time of the Ordovician, pushed up 29,000 feet up into Mount Everest. The Paleogene was also the time that a particular group of land mammals made their way back to the sea and eventually became the whales, which shows you how dramatically life can change over time. So the last geologic period of the Cenozoic that we're in now is the Neogene. So during the Neogene, the mammals continued to diversify, but the Earth continued to get colder and colder. So when you hear about ice ages, many of the ice ages that you've probably heard about, and the animals like saber-toothed tigers and giant ground sloths, mastodons lived during the time of the ice ages. And of course, the Neogene was the time that humans show up. So our own species, Homo sapiens, show up in the fossil record between 200 and 300,000 years ago, and we began to spread out of Africa about 70,000 years ago. Some went along the coastline all the way to Australia, some went into Northeast Asia and crossed the Bering Straits. Others went into Scandinavia, and my own ancestors, as I had my DNA traced, went up into Scandinavia just as the last ice age melted about 12,000 years ago. So some scientists have proposed that we name the current geologic period the Anthropocene, because we're having such a big impact on the environment. And remember what we've seen in Earth's history. You probably can't take me serious with the horns. But anyway, remember what we've seen. One species can have a dramatic influence on the planet. Remember the stromatolites. So in our case, we're basically reversing what happened during the Carboniferous, when all those forests were sucking CO2 out of the environment. Now we're burning the remains of those forests in the form of coal and releasing the carbon dioxide back into the atmosphere. Carbon dioxide levels have risen 35% since the Industrial Revolution. And what about the impact of humans? Well, in May of 2019, the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, which is made up of 400 experts from 50 countries, did a vast amount of research, and this is what they found about human impact. 1 million species are at risk of extinction. 1/4 of plant and animal species are at risk. Ocean pollution has increased 10 times since 1980. And so I think what we can realize from the geologic record, by looking at the Earth's biography, we get great perspective. And that perspective of what's happened in the past can help us plot a wise course for the future. What we can learn from Earth's history is basically two things. The Earth changes, not overnight. Changes are sometimes slow, sometimes faster, but species have to adapt to keep up with that. And amazingly, we're one of the species that's most capable of doing that, but we're not aware of our need to adapt yet. So I think the wise thing to do is to take the long view ahead of us, just as we took the long view behind us, and say, what would be the wisest course of action considering the changes that the Earth has gone through in the past?